Welcome to the deep dive. Now, if you've ever, say, relied on a bridge, maybe driven a complex piece of machinery, or even just stood inside a modern high-rise building, you're putting your trust in something small, often overlooked, the welded joint.
Right. And these joints, I mean, they're absolutely everywhere, critical connection points. But here's the thing, they're also, quite often, the weak link, the starting point for failures, especially under fatigue, years and years of stress. So for engineers, figuring out how long they'll last, it's a major research headache, honestly.
Yeah, a headache because there's this fundamental dilemma, right, in how you analyze them. Engineers, they obviously need safety, they need durability checks, but the tools they have kind of force a choice. Do you go for the super accurate method that's just too complex computationally for anything big? Or do you pick the one that's fast, cheap, but maybe not scientifically sound anymore?
That's it, exactly.
Yeah.
It's that classic trade-off, accuracy versus speed or expediency. And the gap between those two approaches seems to be getting wider. You got these really sophisticated academic models. They need huge computing power, tons of pre-processing work to model every tiny detail. And then on the other side, you have the established industrial methods. They're simple, sure, but many people now think they're, well, scientifically a bit obsolete. They just don't capture the local stress points where failures actually start.
Okay, so that sets the stage perfectly. Our mission today, then, in this deep dive is to look at a new potential solution, something designed specifically to bridge that gap, the ENLO-SED method. It tries to blend the precision of the academic approach with the efficiency that industry absolutely demands.
Yeah, and what's really interesting is that the researchers here didn't just want to compromise. They were aiming for both high accuracy and high speed. To really get how they did that, we first need to understand the pain points, the downsides of each of those existing methods.
Right. Let's start with the academic side then. The sophisticated, high accuracy, but high cost one, strain energy density, SED. What exactly is SED and why is it seen as the gold standard for accuracy and fatigue?
Well, SED is what we call a local method. It's very focused. It doesn't try to analyze stresses across the entire structure. Instead, it zooms right in. It calculates the energy stored within a very small, specific volume right at the tip of the geometrical notch, the weld toe.
Okay.
By concentrating on that tiny pocket of energy, you get a much, much better prediction of when a crack might start.
Okay, so local is key. And to do that in a computer simulation, you actually have to define that tiny volume in your FEM model. The sources mention a specific size, a critical radius, utter channel words. For steel, it's 0.28 millimeters. That's incredibly small.
It is. It's microscopic, really. And that tiny size is, well, it's the root of the practical problem. To accurately model the energy within that tiny radius, you need to use solid mesh elements, sometimes called brick elements. They model the full 3D volume of material. And modeling even a small region with these solid elements takes a huge number of them just to define the geometry accurately near the weld.
Ah, okay. So if I'm modeling, say, a big piece of equipment, maybe it has 100 welded joints. For each one, I have to zoom in, define this tiny 0.28 millimeter zone, make sure it's meshed correctly with solid bricks, and then the computer has to solve for maybe tens or hundreds of thousands of these elements for each joint. That sounds like a massive bottleneck before you even run the analysis.
It absolutely is. Significant computational demands, yes, but also a lot of user intervention needed in that pre-processing stage. It makes the standard SED approach pretty impractical for large industrial projects with tight deadlines. It's highly accurate, no doubt. Great for research papers, but not so great for production design cycles.
Okay, so that's the accurate but slow side. Let's jump across the gap. The element nodal load method, ENLO, the industrial favorite. The quick and dirty option.
Well, quick is definitely the key word. It's preferred because it's fast. ELNO estimates stresses at critical spots using the element nodal loads, basically the forces and moments that the FEA software calculates anyway. And crucially, the stresses it derives are largely mesh insensitive. That's a big plus. It manages this because it relies on much simpler shell elements.
Shell elements. Can you just quickly explain the difference for listeners? Solids versus shells.
Sure. Think of it like this. Solid elements, those bricks, they model the entire 3D volume, like building with tiny Legos. Shell elements, though, they just model the surfaces, like using thin sheets of paper or cardboard. They're way, way easier to create a mesh with, especially for complex shapes. And since ELO uses these shell elements, you need far fewer elements overall, much lower computational demand. The stress calculation itself is purely a post-processing step. It happens after the main simulation runs. That simplicity and speed is why it's built into commercial software packages, like ENCODE Design Life.
Right. Speed, simplicity, automation. Sounds great. The obvious downside, though, is that using those simplified shell models, you're accepting lower accuracy, right? You're making a scientific compromise to get the speed. So we have high cost, high confidence versus low cost, lower confidence.
Exactly. And that's where we get to the breakthrough idea with ENLO-SED. It's the realization that, hang on, if the SED method is so accurate, why can't we somehow estimate its key output, that strain energy, using the inputs from the FAST method, from ENLO?
Okay, now this is where it gets really interesting. How do they actually connect those two worlds? Shells and solids, fast and slow.
The key insight they had, or confirmed, was that the strain energy density right at the weld toe, that critical local spot, mostly depends on the loads very close to that toe. It's not heavily influenced by loads far away in the structure. And this implies that you can potentially use the simplified shell model because it does capture the essential local forces and moments accurately enough. Those are the ENLO inputs.
I see. So the structural stresses, 7 low at 2, which you get efficiently from the fast FEL model, can be used as a proxy to calculate an equivalent strain energy, which they call a FEN. It's like using the shell model speed to predict the solid model's answer, but only locally.
Precisely. They developed a conversion formula to do this. But the real magic, the component that makes or breaks this whole approach, is a special calibration factor, the correlation parameter, called sexacore, that's J.
Core. Let's unpack that. This parameter essentially adjusts or fine-tunes the energy calculated from the simple ENLO stresses so that it matches the energy you would have gotten from the complex benchmark SAD calculation. And it depends on the local geometry, the core shape, and the plate thickness, T.
That's the core idea. And here's the kicker. They perform a calibration step. They ran just one relatively simple reference case, an L-shaped weld, under a specific bending load to figure out the right value for Tech D. The genius, or perhaps the gamble, is taking that single calibrated Tech Z value and assuming it will work accurately for completely different joints and different loading conditions in real industrial scenarios.
Wait a minute. If TXZ was calibrated on just one simple joint under one specific type of load, isn't there a huge risk it won't work for, say, a complex frame structure under tension or shear? That sounds like.
Well, like a potential weak point in the method itself. That's absolutely the critical question. You put your finger right on the key test for this method. If Texing isn't robust, if it only works for that one calibration case, then the whole thing isn't very useful. So the goal of the validation part of their research was exactly that. Can we truly preserve the accuracy of the gold standard SED method while using a massively simplified shell model relying purely on that locally calibrated Texi factor?
Okay, let's see the proof then. They tested ENLO-SED on a pretty common joint, right? A rectangular tube welded onto a plate. You see this kind of joint everywhere in industry, sometimes dozens or hundreds in a single large assembly, so efficiency is absolutely crucial.
Yes. And to directly address the robustness concern you just raised, they deliberately chose different boundary conditions for this test case. Completely different from the calibration setup. They fixed one surface, surface A, and applied a simple 1 Newton point force to another surface, B. Totally different load path compared to the distributed bending moment used to find SED originally. If the DOCD parameter holds up and gives accurate results here, it strongly suggests it can generalize well.
Right. Let's talk hard numbers then, the payoff. Because this is where it could really speed up industrial design. The difference in complexity between the shell model for ENLO-SED and the solid model for standard SED sounds stark.
Oh, it is. Just look at the number of mesh elements. The detailed solid model needed somewhere between, say, 54,000 and 68,000 elements, depending on the exact setup. The streamlined shell model, a fixed 4,200 elements. For all thicknesses they tested, that's more than 10 times fewer elements for the computer to handle.
An order of magnitude difference. And what about the time it takes just to create the mesh, the pre-processing?
Even more dramatic, actually.
Yeah.
Meshing that complex solid model, getting all those little brick elements right near the weld. That took 33 seconds in their test.
Okay, 33 seconds. Doesn't sound like ages, but...
But compare it. Meshing the simple shell model took just 2 seconds. That's 15 times faster. And while seconds might not sound like much, imagine doing that dozens of times for iterations, or across hundreds of joints in a large model. Those seconds turn into hours, even days of engineering time saved.
15 times faster meshing, and the actual calculation time, solving the model.
Also significantly faster. The shell model solved in just 3 seconds. The complex solid model took 15 seconds. So 5 times faster solving time.
Pure speed increase there.
Definitely. But there's another huge advantage, especially during the design phase, that we need to highlight. Think about product development. Engineers are constantly tweaking designs, maybe testing different material thicknesses, right? Let's call it T. With a complex solid model, if you change the plate thickness T, you fundamentally alter the 3D geometry, which means you have to go back and completely remesh the entire CAD model, redo all those thousands of brick elements. It's a major pain, requires lots of user intervention.
Right. Every time you want to try a slightly thicker or thinner plate, you're potentially redoing that 33-second meshing job, maybe more if it's complex.
It's exactly tedious. But with the shell model approach used for ENLO-SED, thickness T isn't part of the mesh geometry itself. It's just a parameter, an input number you adjust in the post-processing calculation. You change T in the formula, and you recalculate the energy using the same simple shell mesh. No remeshing needed. This ability to rapidly iterate on thickness without getting bogged down in remeshing, that's arguably the biggest practical payoff for industry.
Okay, the speed gains, both in setup and solving, and the iteration flexibility, they're undeniable. But playing devil's advocate here, is the fast answer the right answer? All that speed is useless if the accuracy isn't there. How did Winlos actually compare to the benchmark to the collet?
That's the crucial validation. And the accuracy results were really the final piece of the puzzle. They were very positive. The estimated energy from the FAST method, ENLO-SED, it tracked the highly accurate reference energy, ENLO-SED, remarkably well. It followed the pattern almost perfectly all along the weld line, even capturing the stress peaks around corners and such.
And did they quantify the error? What was the actual difference?
They did, and this is the key metric. The absolute error between the fast ENLO-SED estimation and the detailed SED reference calculation was globally less than 8%, usually quite a bit lower, but capped below 8%. So think about that trade-off again. You get high reliability under 8% error combined with that extremely low computational effort. Remember, 15 times faster meshing, 5 times faster solving, easy thickness changes. This combination makes ENLO-SED genuinely feasible for those really large, complex models where managing geometry and huge numbers of joints is currently a major bottleneck.
Okay, so summing up this deep dive then, it sounds like the research really delivered on its core promise. It demonstrated that this ENLO-SED method can predict fatigue resistance specifically for modi crack opening in the study with impressive accuracy, and it does it with massive computational savings. They seem to have found a way to balance that academic rigor with industrial practicality.
It's definitely a powerful proof of concept, yes. But it's also important, as always, to be clear about the current scope. These specific results, this validation, is currently for certain conditions. We're talking full penetration welds, steel plates between 2.5 and 6.0 millimeters thick, and standard 45-degree weld beads.
So the foundation is solid, but there's more building to do. The researchers themselves mentioned future work, right? Extending it to more complex geometries, maybe different materials, and crucially, including other failure modes, like crack initiation under Mode 2 and Mode 3 loading, shear, and tearing modes. That would cover a lot more ground.
Absolutely. Expanding the applicability is the logical next step. But what really stands out to me from this current work is that core finding, that local correlation parameter to actual correlations. The fact that it was calibrated on one simple case but remained robust and accurate under completely different loads and geometry, that's significant. It suggests that maybe, just maybe, you don't always need to model the entire global complexity of a structure in minute detail to predict critical local failures accurately.
That's a really interesting point. It makes you wonder, doesn't it? If this simplified approach, derived from just one calibration, can predict complex local behavior so well across different conditions. What other areas of engineering simulation, areas currently dominated by these huge resource-heavy models, could potentially be streamlined? Are we perhaps over-modeling things sometimes? Maybe we just need better ways to capture the essential physics, the core local dependencies, more efficiently.
A provocative thought indeed. Something for you, the listener, to perhaps mull over next time you're looking at a bridge or a ship or any large welded structure holding our world together.
Thank you for joining us on the Deep Dive. We'll see you next time.